Welcome to CS420, lecture number 18. In this lecture, we're going to add user-defined procedures into our language. Now, we already have procedures or functions that are built in, and those are primitive expressions. In this case, we're going to allow users to define their own procedures. Now, that means we're going to have to introduce two new expressions into our language. One expression will be to create a function, and another expression will be to call the function. So our final syntax will look something like this. Let f equal a new function. The function takes in two parameters, y and z, and it multiplies y by z minus 5. So this is the body of the function. These are the parameters of the function. And that is called a proc expression. So that's the first kind of expression that we have. Now we added let expressions in the last lecture. Now the body is an application expression, and in an application expression we have an operator, or the function we're going to try to call, and then we have our operands, and those are what we're going to pass into the function.
Now the other way that we can call functions is to declare anonymous functions that never get named and then call them right afterward. So this parenthesis is part of our application expression, kind of the same parenthesis in there. The only difference is this is a var expression that's going to look up f in the environment and find our function. In this case, it's a proc expression that will create a function on the fly that never gets named, and then this application expression will call that function passing into an 8. Now, it's important to read through this part here that talks about static scoping versus dynamic scoping. And programmers have pretty much agreed that it makes a lot more sense to use static scoping. We use the variable that was in scope at the time the procedure was created, instead of using dynamic scoping. So what that means is that we have to capture the environment when the function is created. So when our proc expression runs, we want to capture that environment and make sure we have access to all the variables that are in scope at that time. That way, when we call the function and run it later, we're using the same environment. If we didn't do that, we would have dynamic scoping, and dynamic scoping can lead to all sorts of errors where one function creates and uses a variable that erases the variable that another function is using, and that can cause a lot of confusion when variables start changing and you don't see where they're changing just because you happen to call a function. So that's why we're using static scoping. And to implement that, we're going to have to create a closure. And a closure is some code to run, which will be an expression, and an environment to run it in. So we're going to save, when we create a new function, we're going to save the environment that exists at the time we create that function, so that when the function is called, it can use that same environment. So we're going to use define data type to create a closure so that we can store the information we need, which will have our parameter names, the body of the function, and the environment to run the body in. So to implement this, first in our grammar, we're going to create the two new expressions, a proc expression and an application expression. And you can see, because we want commas between our parameter names in our proc expression, that we have a separated list of identifiers, and they're separated by a comma. Versus our syntax for application expressions, they separate their expressions by its space. So we want to have at least one expression that is the operator, and we're going to call that the ratter, and then a list of operands, and they're just an arbitrary number of expressions because we're just separating them by spaces. And you can see when you run scan and parse that it has no problem turning this into an abstract syntax tree. That's a proc expression, and an application expression as well has no problem turning that into an abstract syntax tree. Now you can see right here with the defined data type that we're creating a new data type for closures. Now, the way defined data type works is we have different variants. So the variant's going to be a closure, but the main type is going to be a proc val. So we just copied and pasted this in from our lecture notes. Now, our implementation of a proc expression is pretty easy. A proc expression, the abstract syntax tree, has variable names, or its parameter names. By the way, those are called the formal parameters. When you're creating a new function, the parameter names are called the formal parameters. And then it also has a body, which is the code that we want to execute when the function is called. Now, if you notice, all I do is create a closure. I store the parameter names. I store the body, which is the abstract syntax tree of the expression we want to run. And then I store the current environment that was passed in to eval expression when this program was created. And that's how we're going to capture the current environment. One thing, if you notice, that I do not do is call eval expression on the body. When someone's creating a function, I don't want to run it right then. I want to run it later when they call the function. If I were to call eval expression right now, I'd run the body as they were creating it, and that's definitely not what we want to do. Now we can see when we run a proc expression, what we get back is a closure. So the closure contains the variable names, also the expression that we want to run, which is a primap expression that adds x and y together, and the environment. And if you notice, we have the initial environment that still has the I, v, and x in that we created before, so that we had some variables to play around with before we created a let that allowed us to create our own variables. But this is the same thing as running an expression like this. In Racket, if you notice, when we do that, we get the procedure back. Now, it's not printing out all the details, but this is a closure in Racket. Now let's go ahead and implement application expression. So to start with, an application expression has the ratter or operator and the rands or operands. For now, I'll just take my operator and I'll evaluate it because this is any kind of expression. Now, it better be a function that we call, but our syntax doesn't confirm that it is a function. If we look up at our syntax, it's any expression. So it could be a var expression that finds a function in the environment. It could be a proc expression that creates a function. It could also be a primitive expression, a literal expression, an if expression, and even a let expression. So there's no type checking going on to make sure that this function is actually, or this expression is actually a function. But let's go ahead and call app expression, or run a couple of expressions with app expression in it and see what we get back. So if we just run and we're going to call x, passing in I and v, if we try that, if you notice, I get 10 back because that's the result of evaluating x. Remember, in our initial environment, x is bound to 10. So if we were to try to call 10, that would be an error. We can do the same thing with in Racket. If we try to call 10 with, say, 5 and 3 inside of it, you can see it's giving an error. It's not a syntax error. This is syntactically correct. This is a semantic error because it's trying to call 10, which is a function, which is not a function. So we would hopefully get the same error if they did the same thing. We need to produce the same error. So now what we're going to do, we're still going to evaluate our operator, and then we're going to call that the proc. So this is the function we want to call. Now the ratter is the expression before we've evaluated it, and the proc is the result of evaluating it. We're also going to do the same thing for the rands. We're just going to use the same eval rands function that we've been using for our prim app expression to evaluate all of our rands. And just so we can see what that does a little bit, first, when we run an application expression, I'm going to show you what the rands are, and then we're going to switch this and put it to args and see what happens. So you could see that I'm going to call a function, and what function am I going to call? Well, this proc expression, that'll give me a closure back. And here are my rands, 5 and v. When I run it now, I'm going to print out what the rands are. So when we run this, you see that the first operand is a literal expression with 5 in it, and the second operand is a var expression with v inside of it. Now let's see the result of that. So next I'm going to run the same thing, but instead of seeing the rands, I'm going to see the args, which is the result of evaluating that. So making that change and running this again, we see that 5, which is a literal expression, has been evaluated to 5, and v, which is a var expression, we looked up v in our initial environment, and remember v is bound to 5, and we get 5 back. So what eval_rands does is it turns a list of expressions into a list of evaluated values. Next, let's just see what our proc is. We've already kind of seen that before, but not with this expression down here. So we'll run this with a proc, and we could see that our proc is our closure. So this was turned into a closure from this expression up here. So now what we'll do is we'll do a little bit of checking. We'll check to see if the proc is a proc val. So where does that function come from? Well, that function comes from our defined data type. Remember, it gives us a predicate to check to see if things are a proc val. So if it's a closure, it'll return true. If it's anything else, we'll get false. So just to see that in action, what we'll do is we'll run this expression right here, which is legal because the first expression is a procedure. And you can see that that says no error. And if we run this expression where x is our first expression, x is going to evaluate to 10, and we're going to get the error saying attempt to call a non-procedure 10. So now what we'll do, instead of putting a lot of code right here, is we'll just write a little helper function that will go ahead and execute the procedure or call the procedure. And that function is called apply proc val. And I've gone ahead and pasted it down here, but let's go through this code a little bit. You can see that we have a cases, and cases is used to get the data out of our procedure. There's only one case that it can be as a closure, but we want to get its list of parameters out of the closure. We also want to get the body of the function that we want to evaluate, and we also want to get the stored environment, or the environment that the closure captured when it was created. So you can see that I'm getting the IDs, which is a list of parameter names, the body, which is the function we want to call, and the environment, and I'm calling that the stored environment out of this function. And then what I want to do first is extend the environment. Because we're calling a function that takes in parameters, we got to extend the environment with the new parameters, and we want to bind them to what was passed in for them, which is the args. And then finally, we're just going to evaluate the body of the function in that new environment. So we're extending the environment that was stored in the closure with the new parameter names and the values or the operands that were passed into the function. So we could go ahead and try to run this and see if it works. And it does, because we're passing in 5 for x, v for y. So we evaluate v and find that it's bound to 5. And so that y is going to be equal to 5. And then we extend our environment with x being bound to 5 and v being bound to 5. And then we add the two together. So just so we're not using the same number each time, let's just try this being 8. So x will be equal to 8 and y will be equal to the result of evaluating this, which is 5. And when we add it together, we'll get 13. So now let's run a little more complicated expression. And this is from the lecture notes. We're going to let x equal 5 in, and here's the body of the first let. And in there, we're declaring two new variables. We're declaring f being equal to this procedure and x being equal to 28. And then finally, in that body, we're going to call f, passing in 2 for y and 8 for z. So I'll show you this running, and then we'll get a diagram to see what happens to the environment as this runs. Now the first thing that we'll do, that the program does, is first of all we have this empty environment to start, and then our initial environment comes with I, V, and X in it. And that was just something that we set up so we had variables to play around with before we could declare our own. But now this let expression, the first thing it does is it declares a new variable x, and it sets that equal to 5. So it extends the current environment that has I, V, and x in it, and it extends it with x being equal to 5, and then it moves on to execute the body inside of that environment. Now the body is another let. So the first thing the body is going to do is it's going to run the proc and evaluate the 28 as well. So the 28 will just go into this box right here, but this environment, this box right here, has not been created yet. We just got 28 sitting out there as a result, and we want to eventually bind x to 28. But we also want to run this expression and figure out what it is and bind that to f. So we haven't created this box yet, and we haven't extended that environment yet. But we're going to go ahead and create our closure. So when we run the body, this proc, it's going to create a closure, and the closure is going to have some IDs, which are, in this case, they're y and z. And it'll just store those in a list. Okay. The closure is also going to have a body. And so the body, in this case, will be this expression right here. Okay. And let me use a different color so you can see the body is going to be that expression. Finally, it's going to have an environment, and the environment is the environment that currently exists. Okay, we haven't created that yet, so that's not going to be in our environment. So the environment will be this part right here. So that's our closure getting created. Now after we've created the closure, we'll continue on to create this environment. So we'll bind f to the closure, x to 28, and then we'll extend the previous one. So now that's what our environment looks like. So when we go to evaluate the body, we notice the body of this let. So this let has declared two new variables, and now it's going to evaluate its body. And now that's an application expression. So the first thing it's going to do is evaluate f and see what it is. It will look up f in the environment and find the function. Then it will evaluate 2 and 8. And so those are literal expressions. So somewhere here we'll have the args 2 and 8 that were the result of evaluating these two expressions. And then it's going to extend the environment that the closure captured. So what's the environment that the closure captured? It's this environment right here. So it's going to extend that with the parameters of the closure, which is y and z. And it's going to set y equal to the first parameter, or the first argument. So y is going to be equal to 2. and z is going to be equal to 8. And now it'll run this function. It'll run this body, which is this code, which the body, sorry, I probably pointed that slightly in the wrong spot, but the body is really this right here, not that. So it's going to run the body of the function, which is going to take z. So we're going to look up z, and z is equal to 8. Then it's going to look up x, and it's going to find x equal to 5, not 28. So z is 8 minus 5, so that's going to be 3. And then we're going to take 3 and multiply that by y. Y is 2. And so that final answer will become 6. So that's how the environment looks. Now, one thing to note, if this function right here ends up calling itself, let's say inside of the body, instead of doing this math, it actually wanted to call itself. And so it's just call a function called f. If you notice that the closure, the body, would not find itself in the environment. So we cannot have recursive functions. Because the function, the first time we call it, yeah, we'd find f in the environment and we call it. But when the function tried to find f, it will not find it because f did not exist in the environment. So in order to make recursive functions, what we would have to do is first create this little block right here and extend the environment. Second, create the closure so it could capture that block inside of its environment. And then third, we'd have to update the block to point to the new closure that was created. So that's why recursion will not work using these lets. Now, does that mean we have a Turing-complete language? In order to have a Turing-complete language, we need to have recursive functions. But you can look in the lecture notes of lecture 19 where we might fix this or make a way that we can create recursive functions, and you'll see that there is actually a way using different function calls, and they're called combinators, that we can write programs that will make recursive function calls. So we now have a Turing-complete language. This language that we created in the last couple of lectures can execute any program that's ever been executed in any other language. Now, it might not be the easiest to write those things in, and trying to make recursive function calls, if you look at that combinator, will be really confusing and hard, but we do have a Turing-complete language.